Hello folks, we are on a spree of solving previous year 2020 question paper, and today I, Nikita, will be your mentor, your guide, your facilitator, your catalyst and your teacher for helping you solve organic chemistry NEET 2020 questions. What is the agenda? Agenda is of course solving the questions, but the agenda is not only just solving the questions. Then what else are we going to do? Well, we at BYJU'S ensure that you take learning as an experience. You should fall in love with solving the questions. You should fall in love with solving the previous year question papers. You should fall in love with taking the challenges, solving the questions, and having a great learning experience out of it. So I'm here to give you a great learning experience today. Trust me, together we are going to have a great learning session. So, agenda should be loud and clear. We are going to solve the questions of Organic Chemistry 2020 questions, and we are going to learn, unlearn, relearn, and most importantly, fall in love with learning. Let's get started. So let's get deep into NEET 2020 chemistry paper. And you know that when we talk about chemistry, yes, we have three parts. Part 1 is your inorganic chemistry, part 2, organic chemistry, part 3, physical chemistry, and when you divide 100 by 3, you get 33.33. That's what is the percentage taken care of by the examiner in the previous year 2020 paper. So when we divide 45 by 3, so 45 questions are asked in NEET examination. So when we divide 45 by 3, yes, we get 15 questions. So 15 questions were asked from inorganic chemistry, 15 were asked from physical chemistry, and 15 were asked from organic chemistry as well. What are we going to do today? We are going to analyze the pattern. First, let's get the pattern right. Once you understand the pattern, you will see that the things becomes crystal clear. So let's analyze the pattern. Let's see the chapter-wise analysis, chapter-wise how the questions were distributed. Let's begin. So general organic and organic chemistry, some basic principles and technique together which makes GOC, general organic chemistry. 2 questions were asked. So-called 2 questions were asked. But I want to re-emphasize on the same thing that GOC should run parallel with all other concepts, all other chapters of organic chemistry. GOC is the very foundation on which all the other chapters lie. And hence, if your foundation is weak, the building that you're making on that foundation will be super weak. So it's very important to address GOC properly. What else? Hydrocarbons, the second chapter of Organic Chemistry Class 11, hydrocarbons. Again, one of the very foundational chapters. 2 questions were asked. What else? The first chapter of Class 12th Organic Chemistry, haloalkanes and haloarenes. 1 question was asked. What else? Alcohol, phenol, ethers. Again, 1 question. And the chapter, which is a hub of all different name reactions. The carbonyl chemistry chapter. You have aldehyde, ketones, carboxylic acids. Even the ester is a part of this very chapter. 3 questions were asked from aldehydes, ketones, and carboxylic acids. What next? Amines. 1 question. What else? Biomolecules, one of the very underestimated chapters but very important. 2 questions. Do not underestimate the power of common man and the relevant chapters, but mostly these are the chapters which come at the end, so they're neglected most of the times, but this is the key takeaway from previous year question paper. What's the key takeaway? Check it out. Biomolecules, 2 questions, polymers, 1 question, and chemistry in everyday life, 2 questions. So these 3 chapters are accounting for 5 questions. It makes a lot of difference. Moral of the story, understand the pattern. GOC is the foundation. the last 3 chapters, biomolecules, polymers, chemistry in everyday life, are the most neglected chapters, but very important. So do not do this blunder of neglecting them. So after this chapter-wise analysis, this pattern is what you have observed. We are ready for questions. Let's begin. So let's take a look at question number 1. The question is, paper chromatography is an example of, and your options are A. Partition chromatography, B. Thin layer chromatography, C. Column chromatography, D. Adsorption chromatography. So if your concepts are not clear, this might look very similar, that hey, paper chromatography is maybe adsorption chromatography, or maybe thin layer chromatography because paper is very thin, or is it partition chromatography? So your concept should be crystal clear here. Well, the question is directly taken from NCERT. Not a very difficult question, but a very important question, because chromatography is a very relevant, very important, very useful technique. This is a question which is based on the concept of method of purification of organic compounds. It's a practical chemistry question. It's an analytical chemistry question, and it's a very relevant concept, chromatography. Chromagraphia. The Greek words chroma, which means color, graphia means to write. So are we writing with the help of colors here? No. Chromatography was initially used to separate the pigments, and hence the name chromatography has come. But if I tell you the uses of chromatography now, you will be amazed. Let me tell you, being NEET aspirants, you must know that we use chromatography for testing beverages, for testing drugs, for testing food items, for even creating, the buzzword of today's time is vaccine, right? For even creating vaccine. Chromatography has been of great help for the scientists for the generation of vaccine for Ebola. So let me tell you, this concept is important. So let's do one thing. Let's understand each of the options very well, right? So for that, let's understand why do we use chromatography. So when I say chromatography, it's a very important technique which is extensively used to separate the mixtures into their components, purify the compounds, test the purity of compounds. Okay? So if I have to give you a broad classification of chromatography, I can easily give you a mind map. And if you have a mind map, the navigation becomes very easy. So chromatography can be broadly divided into adsorption chromatography and partition chromatography. Under adsorption chromatography, you study column chromatography and thin layer chromatography. Whereas under partition chromatography, you learn paper chromatography. Okay? And the question from this very mind map becomes crystal clear, but it's not just to make you know the answer. We are not just simply putting a tick on the answer, we are learning through the questions. So let's take each one of them individually. Okay? So let's start with the column chromatography. Few words that you should be well acquainted with before I start talking about the first one, column chromatography, is adsorption. What is adsorption? You know, it's a surface phenomena in which, what do we have? We have a bench over which some species is going to sit on the surface, right? It's not going in the bulk, it's happening at the surface. It's a surface phenomena. So when I talk about adsorption, adsorbent comes, right? Adsorbent, the one which is providing the bench to sit, and adsorbate, one that is going to sit on the bench. So these terms should be crystal clear, and if they are, let's start with column chromatography. What do you see here is a column. You can see what we have here is a glass tube, right? In this, we add we add a stationary phase, which is an adsorbent. So we pack this column with an adsorbent, which acts like a stationary phase. Stationary phase, the name suggests that there is no movement that is going to happen. Stationary, right? So we are going to fill this glass tube with an adsorbent, which will act like a stationary phase. To it, we are going to add a mixture that we are intending to separate. So what is going to happen? We have added the mixture. What may happen is something which is very strongly adsorbed remains at the very top. Something which is less adsorbed comes down, and then what do? We add a particular solvent or an eluent, right? With eluent, you should understand that it's a mobile phase. It is moving, it's traveling from up to below to down, right? And along with it, the component can also move, right? So depending on the component that we need to separate, we can add a suitable eluent. And what do you see after some time? That the component, let's say component 1 and component 2 in this mixture, right? So component 1 comes down first. We separate it, open the stopcock, we separate it. Then we add another specific solvent or a specific eluent to separate the second component. Let's say second component also after some time comes down. And the separation is successful. Column chromatography. A column is used, adsorption is happening. So it should be high definition, crystal clear that how the apparatus looks like, right? The next one now, let's take a look. The next one is thin layer chromatography. That's where, if you imagine a paper being a thin layer, you may get confused and you may fall in the trap of the examiner. So be very careful. You need to also be psychologically ready for things. The options can be tricky, but the answers are always very easy. Let me tell you. So if I talk about the thin layer chromatography, you can see that what we have is a closed jar here. Inside the jar, you can see we have added a solvent. That's the moving phase, the mobile phase. This eluent is mobile phase. It can travel up. The solvent can move up on this thin plate that we can see here. So it's a thin layer chromatography. Why is it called thin layer chromatography? Is the chromatography plate, this glass plate that you can see, this is a glass plate, okay? So is this thin? No, not actually. The name thin layer chromatography is coming from this particular adsorbent that we are coating. It's a 0.2 mm approximately thick layer that we coat over the suitable sized glass plate. And this now acts like a stationary phase on which the solvent, the components are going to travel up, right? So please observe the apparatus. Be with me. Let's do it together. You can see there is a baseline here. This is called baseline. And just in the middle of the baseline, we are putting the mixture that we are aspiring to separate. Okay? Let's say we have added 3 inks together. And we are planning to separate the 3 inks now. Okay? So we put in the very center of this baseline that we draw with the help of a pencil at times, and we put a dot in the center of the particular mixture that we want to separate. Ensure one thing, that we are adding solvent here. With solvent and this mixture that we have put in the center, it should not merge, mix together. The baseline should be a little above the solvent. So be careful about that, right? Now let's see what's going to happen. Okay, so you've understood that what we are taking here is a glass plate of a suitable size. We are coating over that glass plate an adsorbent, usually silica gel or alumina. How thick it is? It is very thin. How thin? Approximately 0.2 mm thick or thin, however you want to see it. So this is why it's called thin layer chromatography. Again, what is going to happen? Adsorption is going to happen. What is going to happen further after some time? after some time the components will separate and will travel different distances depending on their degree of adsorption. So let's say component 1 travels the lowest distance, component 2 travels the maximum distance, and component 3 will travel even higher distance. And solvent moves, at above all three of them. And by the help of the distance they have actually moved, we can find out RF, retardation factor. So agenda is not just solving the question and putting a tick. Also, along with the question, let's keep addressing all the important questions. So RF is also a very important question that can be asked from here. So keep connecting the dots. Now let's see what's happening. You can see a jar, you can see adsorbent coated on glass plate. We have compound A, B, C in this mixture that we are aspiring to separate. We have solvent, we have made a baseline. After some time you can see as the solvent travels up, depending on the degree of adsorption, the different components get separated at the different lengths. Sample A, sample B, sample C, they are well separated. X1, X2, X3 are the distance traveled by the sample A, B, C respectively from the baseline. And this Y is a distance traveled by the solvent from the baseline. And RF is nothing but the retardation factor. Retardation factor is nothing but X by Y. So for sample A, it will be X1 by Y. For sample B, it will be X2 by Y. For sample 3, it will be X3 by Y. Y is same for all. So can you compare the R factors also? Of course, you're very smart and you can obviously understand that since X3 is greatest, the distance traveled by the sample C is highest and the distance traveled by the sample A is lowest, right? Whereas Y is same. So certainly X3 by Y is maximum and X1 by Y is minimum out of the three, and hence we can also comment on the R factors or the retardation factor. Thumbs up. Now comes the third most important concept for the day, partition chromatography. Partition chromatography, under which we study paper chromatography. The question belongs to this very segment only. So let's see what's going on. What do we have? We have placed a lid. We have here a paper. What is present here? A paper. It's a special kind of a paper. It's kind of a porous paper, expensive paper as compared to a filter paper or something. It is having, water inside it. Water in what sense? If we actually squeeze it, will water come out? No, not that way. Okay, so be very smart here. Here water is acting like a stationary phase. We have this special paper called chromatography paper that we use. Again, the concept is same as TLC. We put a baseline. In the center of that baseline, we keep a drop of a mixture that we intend to separate. Again, we add solvent here, a little below this baseline, and we leave it undisturbed. After some time, you know that what happens, there will be, depending on the degree of adsorption, there will be movement of the components. Because of the capillary action, of course, the movement is upwards and the outcome is you're successful in separation. Okay, so check it out what's happening. So we have this paper in which trapped are the water molecules, right? So paper, solvent front, solvent, lid is there to keep it undisturbed, and you can see solvent front moving, and you can see the separation also happening, right? This paper so developed is called chromatogram. Developed chromatogram. Sometimes you can see it through your eyes. Sometimes you may have to put it in the UV to observe the color separation, or there are different methods depending on what is being separated. Okay? And the bigger and broader agenda is that the principle here is partition chromatography. Partition is happening. Partition, what kind of a partition? Do you understand what is partition? India was partitioned. That means there was some division that was happening, right? Here also, continuously the substances are partitioned or distributed continuously between the liquid phase and the stationary phase. Liquid phase is the mobile phase. By now you've understood. You can see that continuously the substances are being distributed and are partitioned between the liquid phase and the stationary phase. Hence, paper chromatography is a brilliant example of partition chromatography. So the question was simple. Paper chromatography is an example of partition chromatography, thin layer chromatography, column chromatography or adsorption chromatography, and the answer to this question is option A, paper chromatography is very much an example of partition chromatography. Now let's take a look at question number 2, which says, the question is very interesting based on name reactions. Reaction between benzaldehyde and acetophenone in presence of dilute NaOH is known as, and the options are Cannizzaro reaction, cross Cannizzaro reaction, cross Aldol condensation or Aldol condensation. The question of course belongs to the alpha hydrogen reactions due to alpha hydrogen. And the best approach for these kind of questions is, first of all, you should have an eye for which has alpha hydrogen and which does not have alpha hydrogen. So the game shall be over for you if you do not know IUPAC nomenclature here. You should know what is benzaldehyde and you should know what is acetophenone. Let me show you the structures, and the first thing first, let's figure out which has alpha hydrogen and which doesn't. Check it out. So benzaldehyde, you can see there's no alpha hydrogen. Acetophenone, you can see there are alpha hydrogen present, right? So this is the first approach to figure out which has alpha hydrogen and which doesn't. So our benzaldehyde has no alpha hydrogen, acetophenone has alpha hydrogen, okay? And if we know the individual reactions, these individual name reactions, what is specific to them, what is the stepping stone in terms of the alpha hydrogen for them, we will be able to nail this kind of a question in seconds. It was a seconds question. You do not need mechanism for it. You do not need any kind of different understanding. All that you need to know is if there is a carbonyl compound with no alpha hydrogen and if there is a carbonyl compound with alpha hydrogen, what is a possibility? Is it a possibility of a Cannizzaro reaction? Is it a possibility of Aldol condensation? Or is it a possibility of cross Aldol condensation? Or is it some other kind of a name reaction possible here? So I'm sure the clue to SMART is more than enough. And here, when you see this one carbonyl compound with alpha hydrogen and the other with no alpha hydrogen, okay? Yes, there is a possibility of cross Aldol condensation. But the clarity will only come if you know what happens in others, right? So let's do one thing. Let's take a look at all the different options which has been given to us, because the knowledge of alpha hydrogen, the reactions that involve alpha hydrogen, the knowledge of that is prerequisite to solve a question like this, which has actually been picked up from NCERT as it is. Question is easy, but let's look at the approach. Check it out. For option A, Cannizzaro reaction, what do we need? We need no alpha hydrogen. The carbonyl compound should have no alpha hydrogen. That's the prerequisite. And you know what happens in Cannizzaro reaction. There is disproportionation reaction that happens. It's a self-oxidation reduction reaction that happens. There is the base that you add to the carbonyl compound with no alpha hydrogen, and what do you see? One component gets oxidized, the other gets reduced. So it's a reduction and oxidation happening simultaneously, right? So I'm sure A is ruled out because one has alpha hydrogen in the question which is given to us. What about option B? Cross Cannizzaro reaction. Here what do we have? In cross Cannizzaro, we need to have two different carbonyls with no alpha hydrogen. So when we had the Cannizzaro, we had the same carbonyl with no alpha hydrogen. Now what do we have? We have two different carbonyls with no alpha hydrogen. So again, no alpha hydrogen, no, that's not the case. Acetophenone does have alpha hydrogens. So cross Cannizzaro is also ruled out, isn't it? Right? So we know that in Cannizzaro, here also there will be disproportionation that will happen. Right? So let's rule this out. There's no such self-oxidation reduction which is asked. So let's rule out option B as well. Let's look at option which is talking about aldol condensation. Aldol condensation. Two same carbonyl with alpha hydrogen. Same carbonyl? No, we do not have same carbonyl here. And when we have different carbonyl compounds, right, that's when the possibility of cross aldol comes into picture, isn't it? So if I talk about this option, which is talking about cross aldol condensation, we have here two different carbonyls with at least one carbonyl compound with alpha hydrogen, right? So that is where the possibility of cross aldol comes. Let's say if I have two compounds, both have alpha hydrogen, then 4 possible products can be formed. But in this very case, when only one has alpha hydrogen, so it can react with its own self and give you a product. It can condense with its own self and give you one product, and it can show reaction in this way where one particular compound with no alpha hydrogen is reacting with one particular carbonyl compound with alpha hydrogen, and one product is there which you get. So 2 possible products, which means cross aldol is possible, right? So in our case, we had benzaldehyde and we had acetophenone. We know that in acetophenone there is alpha hydrogen present, right, which makes it eligible for the very cross aldol condensation, right? So let's see the reaction, how it is going to happen. In the presence of the basic medium OH minus, what is going to happen is you get this major product, benzyl acetophenone. Benzyl acetophenone. Okay? So please check. This is the major compound. Why is it? The mechanism will tell the right answer for this. So be with me. Let me show you how it is happening. The mechanism should be crystal clear. Okay, that can also be asked. So with the question, let's clarify the mechanism. Let's take benzaldehyde here. Let's take acetophenone here. Let's understand that 2 different carbonyl compounds react. Cross aldol takes place. So how is it taking place? The mechanism is right here in front of you. Acetophenone. There is basic medium OH minus. See what's going to happen, right? We have OH minus which can abstract the acidic hydrogen, right? So that what do we get here is, please check, this is what we get. A nucleophile is ready in front of you. Okay, there is a nucleophile which is ready in front of you. This carbon is carrying a minus, and this minus can come here, this can come here. There is possibility of resonance stabilization. Yes, everybody, can you observe what can happen is a minus M here. Anyhow, we know that the carbon-carbon bond will be formed. So carbon with the minus is going to attack now to the carbonyl compound, and there will be nucleophilic addition that will happen, isn't it? So see now what is going to happen. After this particular species is ready, this carbon with the minus is ready, what is going to happen next? Check. We have the carbonyl compound. What am I taking? I'm taking the same carbonyl compound, same acetophenone, right? And what do you see? You can see the carbon-carbon bond getting formed. The nucleophile attacks this carbon out here, which is electrophilic in nature because of the polarity out here. We have CO bond. You know that this carbonyl bond is polar. You know that here this can come here and this becomes electrophilic in the need of electrons. Nucleophile is ready here for the attack. So nucleophilic addition reaction takes place and this is what you get. Okay, the reaction has happened. The carbon-carbon bond has been formed. Oxygen is ready with a minus here. But not for long. We have H plus coming from here. Check it out so that what do we get? Here we know that the base is acting like a catalyst. It's not consumed in the course of reaction. So you can see that OH has been attached here. Final thing is this that we have got, and the reaction doesn't stop here. You know that dehydration can happen, can take place. So check it out what's happening, right? After this has been formed, OH has been formed. What have we got? We have got, with respect to carbonyl, this is alpha position, this is beta position. So we have got a beta hydroxy carbonyl compound, right? And now, after dehydration, you can see that we may get alpha beta unsaturated carbonyl compound, isn't it? So let's see the step 2. Also, what may happen is we may do the same nucleophilic addition now, not to an acetophenone but benzaldehyde. And my question here is also for you to understand that benzaldehyde acetophenone, which is going to be more reactive towards the nucleophilic addition reaction, a ketone or an aldehyde. You should know that aldehydes are more reactive towards the nucleophilic addition reaction as compared to ketones because of 2 factors, electronic factors as well as steric factors. In ketone, from 2 places, these 2 huge electron clouds are present, which will not allow any kind of a nucleophile to come and attack, right? As well as electronically also, because of the there's this alkyl group also present. So because of the alkyl group, the plus I effect present, electronically also ketones are relatively more stable. So the 2 points out of benzaldehyde and acetophenone, you must understand benzaldehyde is more acceptive, more receptive, more reactive towards the nucleophilic addition reaction. So that's why the major compound will be coming from here. So take a look. What's going on? Again, the nucleophile is ready for the attack. This electrophilic carbon is also ready for the attack to happen on it. What happens is, this is what that happens, right? Finally, what you get is O minus. O minus takes the H plus so that you get a beta hydroxy carbonyl compound like this. And then you know that the reaction out here is possibility of beta hydroxy carbonyl compound. All the difference there is here aldehyde, benzaldehyde has been receptive towards this nucleophilic addition reaction. In the previous one, a CH3 was here. That's it. That was the only difference. So if we compare, actually this is step 3 now happening. Please check dehydration on heating so that we get alpha beta unsaturated carbonyl compound. So check it out, this is the product that you get. But whereas the same nucleophile was attacking on the benzaldehyde, the alpha beta unsaturated carbonyl compound that we get is different here. And in fact, the product that we are getting here is the major product, isn't it? So you can see this is the carbonyl compound, this is alpha position, this is beta. So between alpha and beta, we have a double bond. Hence, we are calling it alpha beta unsaturated carbonyl compound. With respect to carbonyl, you're looking at alpha and beta. Perfect. And if I compare the two, you know that the major one is when benzaldehyde was undergoing nucleophilic addition reaction. So this particular species is the major one that we are getting in B. This is major, and now you know why. You know the name also very well. This is benzyl acetophenone, which becomes the major compound. So 2 of the compounds are possible here. If we would have taken 2 carbonyl compounds, both with alpha hydrogens, then 4 possible products were possible, right? Here, 2 possible products are there, right? But makes it eligible for cross Aldol. 1, The carbonyl compound with the alpha hydrogen with itself, and the other one with the carbonyl compound with no alpha hydrogen. So in this case, the same nucleophile, which was this, isn't it? COCH2 with a minus. So same nucleophile could attack acetophenone as well as benzaldehyde. And when it was attacking benzaldehyde, this is what we get, which is the major product of the reaction. Okay, so the answer to this question is, of course, reaction between benzaldehyde and acetophenone in presence of dilute NaOH is known as, and the right answer to this question is cross-aldol condensation. Now let's take a look at the next question, which is very simple. Again, as it is a NCERT question, the question is, which of the following is a cationic detergent? You know it or you do not know it. There is no midway. So the moment you see the options, you should realize the right answer rather. The options are option number A, sodium stearate, option number B, cetyl trimethyl ammonium bromide, option number C, sodium dodecyl benzene sulfonate, option number D, sodium lauryl sulfate. Well, when you hear the term sodium stearate, you understand that the cationic part is sodium and the anionic part is going to be a huge hydrocarbon chain with some ion, right? Cetyl trimethyl ammonium. So here you realize that this is the cationic part, right? And this is the anionic part. Sodium dodecyl benzene sulfonate. Again, you realize that the sulfonate, again an anionic part, is present here, right? Sodium lauryl sulfate. Again, you can see that the sulfate is involved here. The anionic part sulfate is here. So, little common sense and you can do this question, let me tell you, even if you do not remember the examples of the different synthetic detergents. So the question belongs to the very topic of synthetic detergents. Synthetic detergent, when I tell you, can be categorized into anionic, cationic and non-ionic. Detergents, you know, is a very special type of a soap which can work in hard water as well. Soaps fail in hard water, but detergents are useful, can work in the hard water as well. Of course, needless to say, will work in soft water as well. So detergents, what are they? Everybody knows, the moment we hear the term detergent, the washing, cleansing agents come in our mind. With the help of this question, let me break the myth of yours of relating detergent only to washing the clothes. No. Let me show you different examples and the answer will automatically come your way along with a lot of insight. So let's check it out. When I talk about detergents, a detergent is a surfactant or a mixture of surfactants with cleansing properties in dilute solutions. Basically cleansing agents, right? So when I talk about the synthetic detergents, of course, there are three kinds: anionic, cationic, non-ionic. Let's see all three of them individually, one by one. Let me start up with the first one, which is a part of our question, the cationic detergent. Cationic detergents are quaternary ammonium salts. And the moment you know it, you know the answer, right? Quaternary ammonium salts. Nitrogen, whenever is making 4 bonds, you know, a plus comes over it. Ammonium salt. So there has to be an anion followed by this ammonium salt, right? So usually their anion can be acetate, chloride or bromide, right? The important part of this cationic detergent is that they have germicidal properties. They kill germs and they're expensive, so their usage is also very limited. If you have been using conditioner after shampoo, pick up the conditioner and check out what is present there. Is there any kind of cationic detergent present there? Ma'am, what are you saying? Are we using detergent on our heads? Yes, you use detergent on your heads. Okay, so check out what is present in your conditioner. You will find cationic detergent there. The example, which is a part of your options of this question, is cetyl trimethyl ammonium bromide. And with this question, let me also take an opportunity of decoding this IUPAC name written out here. Cetyl group. What is the cetyl group? This huge hydrocarbon chain that you're observing, right, is a cetyl group. How many methyls do you see? 3 methyls you see. So trimethyl. Okay. What do you see? Nitrogen making 4 bonds. So it's an ammonium ion. So ammonium. And the anion here is bromine with a minus. So it is called bromide. So decode the terminology and just do not cram as it is. Be logical, be skeptic, be rational. Doubt things. And that's what makes you scientific, right? The scientific approach is to be rational, to ask questions. Why is the name it is? Okay? Everything lies in a name. What's in a name? Everything is in the name, right? So be very careful, decode everything and understand. So check it out, ammonium, right? Nitrogen making 4 bonds. This is the cetyl group. The trimethyl groups, the 3 methyls are here, and we have bromide. So the name is also crystal clear. Now let's move on to the anionic detergent. Okay? The name suggests the anionic part is going to be, the part which is having this huge hydrocarbon chain. You will realize it the moment I read it. Anionic detergents are sodium salts of sulfonated long chain alcohols or hydrocarbons. Okay? So check it out. What do we have? We have sulfonate here. Please see. Benzene, sulfonic acid, SO3H. If you replace that H with a sodium, it becomes sodium salt of sulfonic acid. Check out the sodium salt of sulfonic acid. Check out this huge hydrocarbon chain. Count the number of carbons in this huge hydrocarbon chain. You can pause the video and check for yourself that there are 12 carbons. Dodecyl. The name also becomes crystal clear. Do means 2, decyl. After 10, we use dec. So, ensure dodecyl. The hydrocarbon chain is also what you're analyzing. You can see there's a minus coming here. It's an anionic detergent hence. So, sodium dodecyl benzene sulfonate is a very well example of the anionic detergent. Okay? The third one is the non-ionic. What is this? Non-ionic detergent, like the name suggests, there are no ions involved here, right? They do not contain any ion in their constitution. We get that from the very name itself. Let me show you an example. Look at this. We have huge hydrocarbon chain yet again. What is it? Polyethylene glycol stearate. Okay, this is a non-ionic detergent. Have you ever washed utensils? If you have, you will realize that in the utensil dishwasher, that dishwashing liquid contains non-ionic detergent, which may be this, which may be any other non-ionic detergent, but do check for yourself, right? Whereas anionic detergent you will commonly find in toothpaste. So their uses are also very important and hence I am highlighting them. Cool? So, question was simple. When I talk about this question, which of the following is a cationic detergent, I am sure you've already realized the right answer to it. Is it sodium stearate? No. Is it cetyl trimethyl ammonium bromide? Yes. Is it sodium dodecyl benzene sulfonate? No. Is it sodium lauryl sulfate? No. It's a non-ionic detergent rather. So the right answer is, of course, you've already understood. But before I proceed to the next question, let me tell you one very important thing. Right answer you've already understood is nothing but option B. But the important thing that I want to highlight here is detergents, all of them, the common thing is long hydrocarbon chain. And if these hydrocarbon chains are very long, bacteria find this very difficult to degrade these long hydrocarbon chains, making it non-biodegradable. Okay? And very recently, Bangalore was in news for some not very good reasons. Bangalore was in news because of foaming that took place in a lake. And the foaming was to such a large extent. What is foaming? You understand foam. You apply it on your face. So imagine that kind of a foam coming out of lake, of water bodies, of let's say river, of let's say streams. So why is that foaming happening and reaching the households as well? To such an extent the foaming happened in Bangalore. So the reason is detergent. Like I told you, these hydrocarbon chains are large enough and bacteria find it difficult to decompose, and even after the water treatment, even after the waste treatment, they are still retained, and hence foaming happens, right? So what is the outcome? How do we take care of this big problem? It's a big problem if you see it. So the way in which we can tackle it is use as small hydrocarbon chain as possible and it becomes degradable. So take care of the environment also. Let's move to the next question. Okay, now this question says elimination reaction of 2-bromopentane to form pent-2-ene is beta elimination reaction, follows Saytzeff rule, is it a dehydrohalogenation reaction, or is it a dehydration reaction? And the options are given to you: ACD, BCD, ABD and ABC. Okay, so basically we need to find out everything that's happening when we are talking about this 2-bromopentane, a haloalkane, converting into alkene, a conglomeration of haloalkane chapter of class 12th and hydrocarbon chapter of class 11th. Right? Now, how is it happening? This is also something we need to be careful about. So you know that when we talk about elimination, there can be two mechanisms, E1 and E2. E1 mechanism, you already know it takes place via formation of carbocation, and stability of carbocation plays a major role. What about E2 mechanism? E2 mechanism, bond breaking and making occurs simultaneously, and what we get is a transition state, and it's a one-step thing that happens. And what do we get? We get from a haloalkane, we can get an alkene, right? But I do not want to indulge myself into explanation of E1 and E2 in this question right now. Okay, so let's keep it simple and let's connect the dots well, because question is very simple. Okay, the question is beta elimination, so we should know what is beta elimination. We should know what is Saytzeff rule. We should know what is dehydrohalogenation, and of course we already know dehydration. I had dehydration today. Loss of water, right? So things are very simple. NEET is always a very simple exam. By now you have already realized it. The examiner may only play with your emotions, which is what we are battling against, which is what we are getting prepared for. So let's get started and see the approach for this question. So the question belongs to, of course, you've understood already that the question belongs to elimination, right? Elimination reaction. So let me start by addressing what is this alpha beta thing, right? Please observe the atom of interest here is bromine, okay? We look for a group of interest or an atom of interest. Here, the atom of interest is bromine, and the carbon which is directly attached to this atom of interest will be called alpha carbon, and the carbons which are directly attached to alpha carbon will be called beta carbon. The next to the beta carbon will be called gamma carbon, and the next will be called delta carbon. But let's restrict ourselves to alpha and beta for now. So this is of course the alpha carbon, the carbon directly attached to the atom of interest. What is the beta carbon? Of course, these are the two beta carbons that we may have, carbon attached directly to the alpha carbon. Perfect. Now what to do? Now let me give you a general reaction without getting into the mechanism of E1 and E2. So if I give you a general, simple, basic, let's keep it very simple but very intelligent. Okay? And you smart generation out there, be with me and see what's happening in a general sense. Take a look. What do we have? We have at the beta carbon, we have a hydrogen. At the alpha carbon, what is directly attached is this atom of interest, halogen for us. And what may happen is, you can see what may happen is HX removal in order to get an alkene. Check it out, isn't it? HX needs to be removed in order to get this kind of an alkene, right? So if I talk about, a base that we are using, we generally use until and unless mentioned. Whenever we want, let me give you a hint here, Hoffmann product, a bulky base will be intentionally mentioned. If not mentioned, we take care that it's a base that is maybe ETO minus or KOH alcoholic. That's generally what we take, right? So until and unless not mentioned, don't use much of your brain by assuming that it's a bulky base, let's say this kind of a base. Okay, if this is what you're assuming, your answer to this question will be totally different. So be very careful. Until and unless bulky base is not properly mentioned, the general bases that we take is like this, ETO minus, right? Or alcoholic KOH. So let's say we have this ethoxide base. Now base is always in a hunt of hydrogen, is always in a hunt of acidic hydrogen or a proton, right? So the moment it finds a proton, what will it do? Will accept it and become ETOH if we are taking ETO minus as our base, right? So check out what's going to happen. Check out for yourself what's happening here. Look at this. The base found its counterpart hydrogen, and what is going to happen? Look at this bond that you see between the carbon and hydrogen. You can visualize it like going here and Br minus leaving, right? So what is the outcome is finally the removal of HBr, and the reaction happens via E2 mechanism, though elimination mechanism was not the need of this question here, right? When we talk about E1 mechanism, the carbocation stability plays a major role. When we talk about E2 mechanism, bond making and breaking occurs simultaneously and we get a very high energy transition state. And here this is what we are trying to show you, that here bond making and breaking is occurring simultaneously and the mechanism is via E2 mechanism, so that what we are getting is an alkene. An alkene here is substituted alkene or less substituted alkene or more substituted alkene. You should have a vulture eye for that as well. Okay, so out here you can see that I'm showing you this hydrogen getting moved and not this one. The base could have attacked this one. Had it been bulky base, yes, the terminal hydrogen would have been gone, let me tell you very frankly here. But now that we have ETO minus, yes, we have two possibilities. One is this one and one is this one. So H1 will go or H2 will go. This is what you have to decide for yourself, and that will decide for whether the product is Saytzeff product or Hoffmann product. So concepts coming your way, the question is simple. So if I take it individually, step by step, let's take a look. We have already understood that HX has been eliminated. And elimination of HX, out here HBr. If we decode this statement, elimination of HBr, if we decode it, if we understand what the organic chemistry definition here is trying to tell us, we will be able to decode it very well. Elimination is D, H is here hydro, Br is here halogenation, dehydrohalogenation, removal of H and X. So removal or elimination of HBr. We can say that yes, dehydrohalogenation is happening. Is it removal of water happening here? No ways. We can't see any water getting removed here. What is rather being eliminated is HBr, right? So check it out. Dehydrohalogenation. Now, if I talk about the two hydrogens, H1 and H2. Perfect. Can H1 get removed? Yes. If the base would have been bulky, H1 would have been going, I bet. But can H2 be removed? Yes. H1 be removed? Let's take both the possibilities, right? Let's question everything. So, when H1 Br removal is happening, what we are getting is alkene at the terminal position, whereas when H2Br is removed, we are getting alkene, which is a non-terminal alkene here, right? Hoffmann product happens in very specific cases, like one of the cases that I just mentioned, that the base should be bulky, right? Whereas Saytzeff product is generally the major product. What is a Saytzeff product? More substituted alkene. Wherever the major product formed is a more substituted alkene, we say the Saytzeff product is formed, right? Whereas less substituted alkene, if it is formed, we say Hoffmann product is formed, right? So, why is it that Saytzeff product should be the generally formed major product? Why? Why are we saying this? Because the moment you see alkene, please do remember, whenever we see a double bond, hyperconjugation should strike the doors of your mind. And if hyperconjugation comes in your mind, alpha hydrogen comes in your mind. The moment you see double bond, yes, the adjacent carbons if are present and there are alpha hydrogens present, more the alpha hydrogen, more will be the hyperconjugative structures and more will be the stability. And life is all about stability, you already know. So is organic chemistry. So what we are going to get, the major product is going to be the Saytzeff product, right? So let's test all the options which are given to us. So the first thing, is it beta elimination? Indeed, it's a beta elimination. The hydrogen which is being removed is at the beta position. Hence, it's of course a beta elimination. It follows Saytzeff rule, yes. Is it a dehydrohalogenation? Yes. But nowhere we saw dehydration happening. So beta elimination, a thumbs up. Saytzeff rule, a thumbs up. Dehydrohalogenation, a thumbs up. Dehydration, a thumbs down. So the right answer to this question, of course, becomes option D, that is A, that is B, and that is C. The right answer to this question becomes option D. Now take a deep breath and get ready for the next one, which is, which of the following amines will give the carbylamine test? I asked you to take a deep breath for a reason. You will just realize. The options are given to you and these are the 4 options. The question is simple. The question belongs to the simple topic of test of amines. And when I say amines, of course, you know the 3 different types of amines. What are those? The degree of amines. Do you remember? Let's take a peep into it. Check it out. So degree of amine, it depends on the number of carbon through which nitrogen of amine is directly attached. Okay, if it is attached to only 1 carbon, nitrogen is attached to only 1 carbon, it's a 1 degree amine. Nitrogen is attached to 2 carbons, it's a 2 degree amine. Nitrogen, if it is attached to 3 carbons, it's a 3 degree amine, right? So let's test the degree of amines here. Look at this. What do we have? Aniline. What do we have? Nitrogen attached to 2 hydrogens and 1 carbon of the benzene. Perfect. Let's take a look at a 2 degree amine or a secondary amine. Check it out. So look at this, nitrogen attached to 1 carbon of the benzene here and 1 methyl group. So 2 carbons and 1 hydrogen. So this makes it a 2 degree amine or a secondary amine. Let's see how a 3 degree amine looks like. Nitrogen attached to 3 carbons. It's a 3 degree amine or a tertiary amine. And the moment I say carbylamine test, you should know that which degree of amine will give a positive test. Okay, so when I talk about the carbylamine test, yes, it is used to distinguish 1 degree amine from 2 degree amine and 3 degree amine. Before I start telling you what is formed in this carbylamine test, what happens in a carbylamine test, it's very important for you to understand that what are distinguishing tests, how to call some test as a distinguishing test. So it's very important to address this very question, that what is a distinguishing test? So for that, there are few tests that I want to show you which are very important. So it is an opportunity for me to highlight important distinguishing tests here. One of them is, of course, a test for distinguishing saturated hydrocarbon and unsaturated hydrocarbon. So let's do one thing. Let's take a saturated hydrocarbon hexane and add to it bromine in the presence of carbon tetrachloride, a reddish orangish solution, right? Brownish also at times written, orangish also written. So you can see this kind of a color when we are adding this bromine carbon tetrachloride in a solution, in a compound which is having unsaturation, decolorization is happening. How it happens, you should also know that. What happens is the bromine are going to be added, right? Addition is happening. And what you get is an addition product. So you can visualize that, okay, decolorization is happening. And the moment you visualize that the decolorization is happening, you know that it's a test for distinguishing. It's a distinguishing test. You can observe it from your naked eyes. Okay, so is if I talk about this Bayer's reagent test, you can see that we had a colored compound and that color is now fading off. Maybe some precipitation may happen. Maybe there is some color fading off. Maybe there is a color coming up, appearing. All these changes should be distinguishable from the naked eyes. That's what we call as a distinguishing test. But when I talk about carbylamine test, you have to have a good smelling sense. So a corona patient would never get to know this test. So this can be used to test whether a person has corona, because many complained that their smelling apparatus has failed. They can't smell anything. Have you heard people complaining the same? People who got inflicted with corona could not smell. But here, your smelling sense has to be perfect. Even if it's minutely good, you know that this foul smell that comes from this test will immediately test your smelling power. It is going to give you a very, 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 very foul smell. So let's see what's going to happen. Check it out. What do we have? We have a primary amine. Perfect. To this solution of primary amine, we are adding chloroform, CHCl3, chloroform, okay. And we are also adding alcoholic KOH. What we're going to do is then we are going to heat the solution. Please take care that it's away from you, and there is a very, very foul smell that comes. How foul? Absolutely stinky. Ill smell comes, ill-scented smell comes, very stinky smell comes, and this gives us a test, a distinguishing test that yes, primary amine is present. What will happen if a secondary amine is there? Let's see. Now what do we have? We have in the test tube a secondary amine. So in the test tube we have secondary amine. We are going to add same chloroform and we are going to add alcoholic KOH. We are going to heat the solution and we are going to waft it. We are going to try to smell it, and you will see that no smell is going to come. Okay, and this proves that it's a secondary amine or a tertiary amine, but it's not a primary amine. Okay, perfect. What about the tertiary amine? Of course, you can extrapolate it to tertiary amine also, that in a tertiary amine also, if we do the same test, what do we add? Chloroform. What do we add? Alcoholic KOH. Again, what do? We heat it. We try to smell it. We try to waft the smell, and if no smell comes, then of course it's not a primary amine yet again. You should know the reaction also very well. Take a look at the reaction now. 1 degree amine will react with CHCl3 in the presence of this KOH, potassium hydroxide, and what do we get? We get RNC, isocyanide group is what you can see here, right? So what you get is RNC along with KCl and water, and this isocyanide group is responsible for giving you that foul smell, that ill smell, that stinky smell, and it is also called isocyanide test for the same reason, because this is the group responsible for this foul smell. Okay, So in the options, what did we have? We had this 2-degree amine, we had this 3-degree amine, we had this 2-degree amine, and we had aniline, the 1-degree amine. Of course, when you see aniline is a 1-degree amine, so it will give you carbylamine test. So if I ask you which is the right answer, which of the following amines will give the carbylamine test, what shall be your answer? Your answer has to be the 1-degree amine, which is option D, the right answer to this question. Now let's have a look at this breezy question with a breezy solution. Which of the following is a natural polymer? And the options are polybutadiene styrene, polybutadiene, polybutadiene acrylonitrile, cis-1,4 polyisoprene. Well, you know it or you do not know it, and you must know it. It's the very important question, because natural polymer means that we are talking about biodegradable polymer. Natural means you're getting it from the natural sources, for example, from the trunk of a tree. So if you know about this natural rubber, polyisoprene, you know the right answer. So polybutadiene, polybutadiene styrene, and polybutadiene acrylonitrile are synthetic polymers, whereas the cis-1,4 polyisoprene is a natural rubber, which is a natural polymer. And if it's a natural polymer, yes, it is biodegradable, and hence the uses are also immense. For example, the bottles from which children, small little, babies, they drink their milk from, so that those nipples are made up of this particular compound polyisoprene. Also, you will see that these are also used, this polyisoprene is also used in rubber bands. So the uses are immense. The compound is biodegradable. So very important polymer, hence you must remember it. And where can you find it? You can find it all over. Have you ever been to Uttarakhand? There are immense ranges of such kind of trees. I'll show you how it looks like. If you haven't visited any of these mountain places where these kind of isoprene compounds, isoprene polymers are found coming out of the trunk of the trees, let me take you to a visit here. Look at this. So how is it coming? You cut the bark a little, and what do you see? The gum coming out from it, flowing from it. And if we look further into it, deep into it, we find that yes, it is cis compound. The two same type of groups are on the same side of the double bond. So it's a cis compound, it's a cis isomer, and you can see it's a cis isoprene. 1, 2, 3, 4, 5. 5 carbons is what you can see, right? And this is the monomer. Repeating unit is what is called cis polyisoprene or cis-1,4 polyisoprene. So the natural rubber is of course D. So the right answer to this question is option D. Now let's check out this question, which says, identify compound X in the following sequence of reactions. What do we have? We are starting with toluene. What are we doing? We are doing halogenation. By adding what? By adding chlorine in the presence of H nu. What do we get? We get X. What do we do further? To the X, we are adding water at 373 Kelvin. Quite high a temperature. And what do we get? We get benzaldehyde. Okay. Alright. So let's see the options for this question. And the options are, you have to find out X. So is X this option A, where we have to the benzene CH2Cl attached? Is it CHCl2 that is going to be attached? Is it CCl3 that is going to be attached? Or is it D, only chlorine attached to benzene? So benzene is common to all four. All that is changing is this group which is attached here. So let's figure out. The concept is, of course, from the hydrocarbon chapter. The mechanism that is used is the free radical substitution reaction. And of course, the moment you see HNu, Cl2, free radical mechanism should strike the doors of your mind, right? So let's do one thing. Let's again try to unfold the mystery behind this question. Let's go into the deeper layers, do the postmortem right, and come out with the right results. So if you observe, it's again a conglomeration of two different chapters. We are getting benzaldehyde, which makes it a chapter carbonyl chemistry, carbonyl compound, or aldehyde ketones or carboxylic acids. And since we are dealing with halogenation reaction, it makes it a question of hydrocarbons also, because to toluene we are doing this halogenation. And since we get this X, which is certainly going to have halogen, now it is up to us to decide whether 1 chlorine will be attached, 2 chlorines will be attached, 3 chlorines will be attached. This is up to us to decide. Or will it be chlorobenzene? But that also gives us a glimpse of haloalkane, haloarenes chapter as well. So great question, because mixing of concepts happening, which is what we love. So let's unfold the layers one by one. Let's first address what is free radical substitution reaction. If chlorine attacks on methylbenzene or simply toluene, in the presence of UV light, substitution happens in the methyl group rather than on the ring. This we know already, free radical substitution. So we need to think of the stability of the free radical. So of course, if you can think of the free radical on benzene, you know it's going to be highly unstable. And everything is about stability. So what about this now? This is of course stable. This is relatively stable. So think in terms of stability and you will be directed towards the right answer, right? So we have this fair idea that free radical substitution is going to happen. And the moment free radical substitution comes, 3 steps should come in your mind. 3 steps. What are those 3 steps? Let's see. When we talk about halogenation, chain initiation, chain propagation, and chain termination. Initiation, propagation, termination. First, a thing will start. Then it will propagate, it will spread. And third, then finally it will come to an end. Right? Let me do one thing. Let me talk about today's situation. What's going on? What is the buzzword? What is the most fearful thing that we all are surrounded by? What is the thing that comes the moment you give a call to somebody? I'm sure you have understood I'm talking about coronavirus. I'm talking about the pandemic. We are in a pandemic situation and we have not come out of it as yet, but we see a bright hope of coming out of it very, very soon. Isn't it? Why? Because we have few things that may help the infection come to a termination. So let's understand first pandemic situation in these 3 steps. Initiation, propagation, termination. Check it out. So everybody knows how COVID-19 came into being. We got it from the bats, and the first infected person, you can imagine that first infected person as the free radical generated. So the initiation has already happened. The person is carrying the virus, but we being social beings, we being social animals, we like to socialize, and that's what was happening. People were socializing, didn't realize that we may carry a virus that can be so deadly, that can lead to a pandemic. And you know that people met each other without any precautions, without any safety, because we were oblivious of the fact that we may even carry the virus. So propagation happened, the spread happened, and the propagation happened to such an extent that almost all the countries were hit with the pandemic, were hit with the COVID-19 virus, right? So there was propagation. But we have science, and with science there is hope. And of course, there were so many researches carried out. We are human beings and we're capable of doing what not, isn't it? NEET examination is a small little thing in this whole journey that we human beings have in front of us. And we, with the help of our cooperation, you can see that in a way we have been successful in overcoming this pandemic time as well, isn't it? So yes, we maintained social distancing, we wore masks, we carried out all the precautions, we washed our hands, and the research helped us in finding out the vaccine. And with the vaccine came the bright hope of the termination of this infection, which has been caused because of COVID-19 virus. So, 3 steps: initiation, propagation, termination. Let's understand it now from the perspective of free radicals. So, chain initiation, look at this. First of all, what do we get is a free radical. After that, propagation. So, once a free radical is formed, it's going to create a havoc. It's going to create more free radicals. Just like one infected person is potentially capable of producing many more chains of infected people, right? So is out here. Look at this. Now what do we get? We get the CH2 free radical. And after that, what's going to happen? You can see that we can get CH2Cl, we can get CHCl free radical, and further chain propagation may happen and we may get CHCl2, we may get CHCl3, right? All different possibilities till the time it finally comes to an end. How in chemistry, in organic chemistry, will it finally come to an end? Either you add something from outside, or there is no sufficient reactant left so that more free radicals could be formed, and they finally come in peace with combining with each other and termination happens. Okay, so you can see that the third step is chain termination. So what is the possibility is we may get a product like this where we have 2 chlorines attached to the carbon and 1 hydrogen attached. Okay, this is one of the products which is possible. Let me tell you, this chain initiation, propagation, termination, whatever this is happening, this kind of a free radical produces multiple products, right? So there is a possibility that we get this particular X. Okay. And now if the examiner is telling us that the product formed is COH, okay, it has given us a great deal of help. How? Because you can see that we are adding water here, okay, and we know that the substitution can happen at the place of chlorine. OH can sit at the place of chlorine, OH can sit. 2 of the hydroxide can be attached to the same carbon, so that what do we get is a, you can see, same carbon with the 2 hydroxy. We are going to call it geminal diol. So what we get is a geminal diol, and immediately when we get this geminal diol, water can easily be eliminated, so that what we get is this benzaldehyde. Okay, so we know that from chain initiation, propagation, termination, from this free radical mechanism, multiple products are possible. But how to determine this X? From retro, from going backwards, looking at the product is benzaldehyde and the probable product is CHCl2, which is going to be our X. So if that's the case, you can understand that 2 OH are attached to the same carbon. So it's a geminal diol. Dehydration happens very easily. 2 OH on the same carbon is highly unstable because there can be easily removal of water molecule, right? So that what you get is a CHO. So when we talk about what this compound X can be, yes, you can realize that the right answer to this question is none other than option B, which is benzene attached to CHCl2, right? So it is a dichloromethylbenzene. The right answer to this question is option B. So I'm sure you had a great learning experience. The remaining question, let's see in the next part. Till then, stay in love with learning. Keep learning.